Pinterest boasts over 400 million monthly active users. Each day, they upload millions of images. The challenge? Enabling users to find visually similar content among billions of images with low latency. Here's what 90% of engineers get wrong when designing a visual search system. The secret is understanding the trade-offs between accuracy, speed, and cost. By the end of this video, you'll know exactly how to build a system that powers visual search at scale, just like Pinterest and Google Lens. Remember this 400 million number. We'll see why it matters when we discuss scaling.
Let's define the requirements. Functionally, users upload an image and receive a ranked list of visually similar images. This requires image feature extraction, similarity matching, and re-ranking. Non-functional requirements? Low latency is crucial, ideally under 200 milliseconds. High availability is a must, aiming for 99.99% uptime. We'll prioritize accuracy, but with an acceptable trade-off for speed. Clarifying questions? Do we support video search? No, just images. What about adult content filtering? Yes, that's a separate module we'll integrate. What about user feedback? We'll incorporate user clicks to improve ranking over time. We also need to consider online versus offline processing for tasks like model training and index building.
Let's estimate scale. Assume 100 million daily active users, with 1% uploading a search image. That's 1 million image uploads per day. Each image is, say, 500 kilobytes. This gives us 500 gigabytes of new image data daily. For QPS, that's roughly 1 IM requests divided by 86,400 seconds equals about 12 QPS on average. However, peak QPS can be 5 times higher, so around 60 QPS. For storage, if we keep images for 5 years, that's 500 gigabytes per day times 365 days times 5 years equals roughly 900 terabytes. We'll also need to store feature vectors. If each feature vector is 2 kilobytes, that's 2 gigabytes per day, adding 3.65 terabytes over 5 years. This means we need to consider data storage and scalability challenges. These estimations highlight the need for a distributed system.
Now let's sketch out the high-level architecture. We'll separate the write and read paths for optimization. The write path handles image uploads and feature extraction. The read path handles search queries. Here's where most engineers make a critical mistake. They don't properly isolate these paths. Remember those 400 million users we mentioned? To handle that volume, we need a robust architecture. We'll use a load balancer to distribute traffic, an API gateway for routing, and separate services for feature extraction and similarity matching. The API will expose endpoints for uploading images, post/API/v1/images, parentheses, image URL, comma, user ID, parentheses, colon, parentheses, image ID, parentheses, and querying for similar images, get/API/v1/search, parentheses, image ID, parentheses, colon, parentheses, image URL, comma, score, comma, parentheses. We use Kafka for asynchronous processing of image uploads because it provides fault tolerance and ordering guarantees. Alternatives like RabbitMQ were considered, but Kafka scalability makes it a better fit. Let's dive deeper into the core logic. For feature extraction, we'll use a convolutional neural network, CNN, specifically a pre-trained ResNet 50 model. Why ResNet 50? Because it offers a good balance between accuracy and computational cost. We might be tempted to train a custom model from scratch, but that requires a massive labeled dataset and significant resources. The CNN outputs a feature vector, typically 2048 dimensions. For similarity matching, we'll use approximate nearest neighbors, ANN search. Face is a popular choice. Why face? Because it's highly optimized for high-dimensional vector search and provides various indexing techniques like HNSW. HNSW is another ANN algorithm. Your interviewer might ask, why not just use exact nearest neighbors? The curse of dimensionality makes exact search too slow for large datasets. Most candidates stop here. Strong answers also address handling visual variations like lighting and angle. We can use data augmentation techniques during training to make the CNN more robust. This involves applying transformations like rotations and crops to the training images. This is where most people go wrong. They don't account for visual variations. The mathematical intuition behind CNNs involves learning hierarchical representations of images through convolutional filters and pooling layers.
Let's scale the system. Caching is crucial.
We'll use Redis to cache the most frequent search results. Why Redis? Because it's fast and in memory, providing low latency access. We'll use a cache-aside pattern. Remember those 400 million users? To handle that load, we need sharding. We'll shard the vector database based on user ID using consistent hashing. This distributes the load across multiple machines and minimizes data movement when nodes are added or removed. For replication, we'll use leader-follower replication for both the vector database and the metadata store. For content delivery, we'll use a CDN like Cloudflare. This caches images closer to the users, reducing latency. Now, at this point, your interviewer will push back. Why not just use a single larger machine instead of sharding? Sharding allows us to scale horizontally and handle increasing data volume and traffic. Bottleneck analysis. The ANN search is the most computationally expensive operation. We can optimize this by using quantization techniques to reduce the size of the feature vectors. Consistent hashing ensures even data distribution across shards.
For reliability, we need fault tolerance, monitoring, and alerting. We'll use Kubernetes to manage our services. Kubernetes provides automatic failover and scaling. For monitoring, we'll use Prometheus and Grafana to track key metrics like QPS, latency, and error rates. For alerting, we'll use PagerDuty to notify us of critical issues. What happens when the feature extraction service fails? We'll use a message queue like Kafka to buffer the image uploads. This ensures that we don't lose data. The worker pool will retry failed jobs. We use Kafka because it provides at least once delivery guarantees. This ensures that even if the feature extraction service is temporarily unavailable, image processing will resume once it's back online.
In summary, we've designed a scalable visual search system using CNNs for feature extraction, ANN search for similarity matching, and a distributed architecture for handling high traffic. Trade-offs? We prioritized speed over perfect accuracy. Potential bottlenecks? The ANN search remains the most computationally intensive part. Next steps? Implementing query expansion to improve search results and incorporating user feedback to refine the feature vectors. We can use online A/B testing to evaluate different query expansion strategies. Practical applications of this system include reverse image search and product recommendation.
Want to master more engineering concepts and coding patterns? Subscribe for weekly tutorials that answer the questions developers face in real interviews and projects.